Okay, let's go for the second part of the class today. Before we go on, do you have any questions? I don't know if it's going too fast or too slow because we have people from that have more experience in reservoir simulation. Maybe this is a little bit slow for you guys, and some people that have no experience with reservoir simulation, so maybe it's going too fast. So I'm trying to going in the speed that is in between well, these two cases. But if you have any questions, for those who never seen simulation, have any curiosity, please interrupt any time to ask questions. And for those who are experienced in reservoir simulations, if you want to contribute to give any information as well, let me know, okay? So we are going to follow talking about some aspects of the grids. Today I'm going to talk about all these aspects and try to go a little bit into the equations. And from next class on, we are going to concentrate more in the equations and then on the well behavior and so on, talking the difference about the black oil and compositional model and so on. So the idea here is not to turn you in experts of writing reservoir simulation equations, but to understand a little bit of these equations in order to understand what they are trying to how they are trying to model this flow behavior and how we can trust these equations when we are using our simulation models. Okay, so this is the main aspect of the. Okay, let's talk a little bit about the grid here. Today I'm just give some examples, but we are give you a specific hints in how to select the grid, okay? But just to give an example, for example, if I have a reservoir that is like this one that we are drawing in the board here, that's not so complex, but is not so simple as well. Here's the mouse. Not so simple. Well, one simple thing we can do is put a Cartesian grid around this reservoir. Of course, as we can see, we are gonna have to deal with some parts of the reservoir that are not so Cartesian. So we're gonna have to deal with this, and there are several ways to do it. Okay. For example, let's assume this part here. For example, we have some blocks here that are not entirely covered by so we have two options here, or we can simply eliminate this part of the reservoir because it's so small, it probably will make no difference. For example, if I have a well here, 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 here, maybe this block is so small compared to the solutions I would have that I can simplify this. Another option that I can have is to assume that the block is this size. For example, just expanding this, but just this part is reservoir. So I'm going to consider the average porosity here, as I have no porosity in this here, but just porosity here. So if the porosity of the porous media of the reservoir is, for example, 20%, in this block is going to be 2% because it's just 1/10 of the block that's covered by the reservoir, for example. So as you can see, this is the option that we are using in this Cartesian grid, which is the most common because it's done automatically. So the grid goes here and here. So every block that can be covered by the boundary conditions here is considered in the reservoir. But the blocks that are like this, for example, if the boundary condition is like this, I consider that the porosity here is half of the porosity of the porous medium. For example, if the porosity is 20%, I'm going to reduce this to 10%. It's the same in mathematical equation. If I have a block of this size with 10% porosity, is the same as I have a block of half size and 20% porosity. There are other ways to do it. One of the most common ways is to use of the keyword in the simulators called net to gross, which is in this case here the net to gross is the amount of reservoir that we have in percentage, for example, of the total size of the grid. For example, in this case, the net gross would be 50%. Or I have 50 of the percent of the block that is reservoir. The other 50 is not reservoir, right? This is common not only in the boundary conditions here, but also I will show you later a figure that shows, for example, if I have a reservoir that have several layers, but in the middle of these layers, there are some other layers that are non-reservoir, for example, and I select this block here, I can use the net, for example, this is non-reservoir, this is non-reservoir, and this is reservoir, and this is reservoir, for example. I can use this net to gross keyword to do the same thing in this boundary here or in this portion here. So I consider that only, let's assume 60% of the block here is reservoir and 40% is non-reservoir, for example. So my net to gross here would be 60%, okay? So for the simulator, in terms of simulation, the equation and so on, it's almost the same. There is no different solution. I can preserve the total porosity of the reservoir and do it by a simple manipulation of this. So I can do this in all these aspects here, not only in the boundary, but also in these layers that are not really reservoirs, like layers with almost zero porosity, for example, or so on. So this is just an example. So I can use a Cartesian grid for a complex reservoir, and I can use some special things that are inside the simulators already. You have to just select this option in order to cover these aspects, okay? And you can see here that you have a lot of blocks here outside the reservoirs, that the only thing that the simulator will do automatically from Petroleum to simulator is, for example, say that these are new blocks. No blocks, then meaning that there are blocks, they are there, but they have zero porosity, so there will be no fluid there, no flow, okay? We can have new blocks in the middle. For example, if I have the same example here, but the size of my block is this one, I don't know if you can see the mouse here, let me put another color. For example, if my block is this size here, and is completely inside a layer of non-porosity layer, then it's a new block as well. So for a simulator, there is no difference between a new block or a block where the porosity is zero. If you set zero porosity, it understand that it's a no block, or it's a block there is no fluid and no flow, okay? And of course, there are other conditions like these ones, for example, that when I will do the upscaling, I have to consider, for example, if this is a ceiling fault, for example, there will have no flow from here to here. So there are some ways to do it. I'm going to show you some examples. There are several ways to do it by using the simulators. But one of the conditions, for example, is that you can set zero transmissibility, or there is no flow in these blocks here, for example. And you can do this by setting a keyword in the simulator, for example. Or there are several ways. So many people criticize too much as Cartesian grids today, but Cartesian grids are not so bad. There are ways to overcome some of the difficulties we have in Cartesian grids, and they are very easy to build, right? There are some advantages, for example, disadvantages. They are very familiar, very easy to generate and manipulate. Sometimes we have these inactive cells. Depending on the way you write the code of the simulator, you have to keep some memory to say that here is a block, but the porosity of this block is zero. So I have to use some memory to keep this information. So sometimes when the codes are not so good, the memory for the Cartesian plots are good. But there are ways to do it, but they're not so bad as well, okay? And sometimes the people say that it's a poor representation of when the geometry is very complex, okay? But it's possible to do it and very easy to put it. And even today, when we talk about more complex grid. Sometimes they are very complex in the vertical direction, but they are Cartesian in the horizontal direction. Like we are saying here, like we are looking this reservoir from the top, and we are putting a grid there that consider the X and Y directions, it's Cartesian, but in the Z directions, it can be another type, as we're gonna show, okay? One way to do it a little bit more complex is to represent a Cartesian grid like this one. If you see this reservoir here in the bottom part, I'm representing this complex reservoir by a reservoir. For example, if you look here, there is not too much difference in a reservoir that is like here, and then I have here a lot of blocks that are net gross less than 100%, for example, or something that look like this. For example, I have a reservoir that goes like this, and my blocks can go like this. In average is a good representation as well, and the difference in the flow behavior is not so big in this case. So I can represent a Cartesian grid by approximating the boundary conditions by linear representations, right? Even here, for example, this photo here, I can represent like this one, okay? Of course, if the grid blocks are very fine, I can represent, for example, here one, I'm trying to represent something like this, right? So the difference is not so big. Of course, if the grid is finer than this one, it's easier to represent this type of geometry. If the grid is coarser than that, then the approximation gets worse and worse every time I'm trying to do. But of course, there are aspects to do it. But you can use the other one that is most common today is the corner points. Okay, the corner points, as you can see here, is representing this geometry much better than the Cartesian grid. Why? Because it's in the corner point, as the name says, used instead of saying how the blocks are distributed, they say how the corners are distributed. So a block, which is something like this. I'm putting a block that's very irregular here on purpose, like so for a Cartesian grid, it's just a block like this, right? But for a corner point, I can change these corners to other points here and make the block not so regular, so it's irregular, and it goes more or less as our precisely as our boundary conditions and faults and things go in the reservoir. So I'm trying to represent this reservoir by using this corner point approximation. So this is was very difficult in the past to do, because instead of one block, I have to put all the points, all the corners, and not so easy to do it. But it's very popular today because all the software like Petroleum and others can generate this corner point automatically, considering all the complex geometry we have in the reservoir. Okay. One difficult aspect of this is they are a little bit more complex to generate and manipulate. They have irregular blocks that causes some problems. I don't know if we have a problem in this example, but let's assume, for example, this region here. If I try to do, you can see that I have blocks that are big like this, or like this, and there are some blocks here that are very small. As we are gonna see in the equations and in the solution of the equation in next week, for big blocks, when I write the conservation equations, the big blocks will have will be much easier to solve than a smaller block. Why? I'm going to explain you in the equations when we get next week, but this is a reality. So for the corner point, one of the major problems we have about this is that we have an irregular grids, and as we have these irregular grids, we have blocks that have very low porosity and low volume. And as we have this, remember that we are discretizing in time, in space here, but also in time. So we have to advance in time. And as you can see, our numerical technique will advance in time according to the estimated errors that we have for the next time step. So for bigger blocks, this time step can be big. But for smaller blocks, as I'm going to show in the equations, this simulation requires the time steps to be smaller. So let's assume, for example, that I have to simulate 20 years, and I'm simulating from month to month, and a Cartesian grid is okay. I can converge the solutions and find the solution every month. But let's assume that I have a corner point, that I have a very regular grid. So instead of running this from month to month, I have to run from day to day. So I have to find 30 solutions in order to advance 1 month. So it must be better in representations. It must be okay to represent better for behavior, but it's much slower than the Cartesian grid. Right? If it is lower, it's not fair to compare this grid with this grid, okay? Because this will run in, for example, 1 hour, and this will run, for example, in 5 hours, I don't know, or 4 hours. So instead of doing this, I could run a much finer grid here of Cartesian grid that would represent these things better, and to run in 4 hours. To be fair, I have to compare 4 hours here with 4 hours here, or 1 hour there to 1 hour there, okay? So be careful when people say, Cartesian grid is very worse, and the corner part is much better, and I just use, okay, the corner part is much better to represent the reservoir, but it has some aspects, numerical aspects and time aspects that in general, they are good, but you have to be careful because sometimes the Cartesian grid is faster, so I can use a finer grid and with similar behavior of these corner point aspects, okay? I'm not saying for you to use corner, just be careful about these comments because people normally would compare this with this. This is not fair because this will run much faster than this one. And also, as we are going to see in the equations next week, the equation that emulates the flow from one block to another is an equation that rewrites that if this is orthogonal, the errors are a little bit smaller when they are not orthogonal like this. For example, if you see here, this is not so bad, but there are some points here that if you're trying to simulate, for example, let's find an example here. From this block to this one, you see that I'm emulating something that is going from this to this. And this, I'm just trying to amplify this, is this block here is one, and this block here is another one. When we're trying to simulate this, we are representing the block by the center of the block, and the flux would do something like this. But I'm writing equations that are writing something like this. And there are, I will explain a little bit in the equation, not too much, but I'm explaining that the errors related to this is bigger than the errors related to when the flow is like this, okay? So, of course, in order to decrease the error, I could use our corner point with a finer grid, but then it would, instead of 4 hours, we'll run 9 hours. So when you compare grids, try to compare the simulation time to run these grids, okay? Okay, let's see. One thing that I'm not gonna mention too much because it's an option that's not being used today, but I believe this will be future, is a defining refinement, is a dynamic refinement of the grids, okay? And, for example, here, let's assume that I'm injecting, I'll take the red part again. I'm injecting, for example, water here and producing in these 4 producers, in this injecting water in these 4 producers here, okay? One thing that is that we want to simulate is how the fluids are moving in the reservoir. Let's assume, for example, that I'm injecting water, and here we are full of water, and here we have just oil, and the water is displacing oil, okay? And of course, in the beginning, I need a bigger precision in the well behavior here, very close to the well. But after some time, the water is moving into this direction, And in this part of the reservoir, I have only water moving. I have a little bit of oil, but the oil is not moving. So my equations could be much simpler. I could do a simplification of the equation. And my grid don't need to be much finer as it was when the water was passing through this region. So there are some simulators that have some codes today that I'm going to explain a little bit of this when I talk about the equations that try to understand which places of the reservoir are more important to solve implicitly and explicitly, like the IEM method that I told you, and which part of the grids are more important to refine. So the refinement would change, for example, here, in this part here, it's more important to have a refinement because the water is displacing oil. In this part here, I have only oil, and here I have just water moving, so I can have a coarser grid. In this part here that I'm trying to capture the displacement of oil, then it's a different aspect. So the grid would change from time to time, trying to capture the behavior of the fluid as this behavior of the fluid changes. And as we're going to see in the equations, there are some main variables on our problems. I'm always trying to solve for pressure and saturation. And these methods are trying to see where the pressure is changing too much or the saturation is changing too much. Then I'm using methods that are implicit, like I told, and the refinement is bigger. And where the saturation is almost constant and the pressure is not changing too much, then I can use coarser blocks, bigger blocks, right? And I can use explicit methods. So that's the idea. The idea of changing between implicit and implicit, which is called IM, is very well implemented in the simulator and is working fine. The idea of implementing this dynamic grid refinement until at least 1-2 years ago that we have tested these options in the simulators, they were not so good. Why? Because they were taking too much time making questions if the region was important to move, changing the grid, changing grid properties, and so on. That normally the computational time using this option was almost the same as simulating everything like refined like this one. So the options was working, but we are not saving too much time in these options, okay? So, but there is, and maybe in a few years, or maybe even now, as you are saying, there are some simulators that have these options that works fine. So once it works fine, would be the best choice for you, right? Because instead of you selecting a priori which blocks will be bigger, which blocks will be smaller, and so on, the simulator would select by himself automatically which blocks would be implicit, which blocks would be explicit, which blocks would be higher and lower, and so on. And it would be much better for the user to let. But even if you use these options, one thing that I'm going to show you that these IM options and these grid refinement options are based on how pressure and saturation are changed. And the user have to select the parameters that we have to use to change from one to another, okay? And this I'm going to talk a little bit when I talk about these options in the equations. But if you have questions, just let me know. Another aspect that is very important is, I put this graph here to emphasize this, is that, for example, if I have if I double the time, the number of blocks, the simulation time is not double; it's much more than that. For example, if I go from 100,000 blocks to 200,000 blocks, the simulation time is not twice. It's much more than twice, because normally we have a grid that is here we are solving 3 equations by block. And there are a lot of things in conversions. When the blocks are smaller, the time steps are also smaller. So when we double the size of the reservoir, the number of blocks, normally we go from 4 to 5 times more. And here's an example where you are showing just where we are changing the number of blocks. For example, from here to here, we are going, doubling the number of blocks, and from here to here is about 4 to 5 times more simulation models. Okay, so this is a very important aspect for you to consider, that when we keep turning the grid more irregular like this, with smaller blocks present in the reservoir, when we are increasing the number of blocks, sorry, this is in Portuguese here, the simulation time goes exponentially up, right? It's not a regular business, it's much higher, as you can see here, right? Here's in the figure, we are seeing the relationship between the number of blocks, sorry, it's in Portuguese, and the simulation time. And as you can see here, is an exponential increase here. Why? Because the computers have limitations in memory. We don't have one equation per block, but normally 3 or even more. The convergence is smaller. When the blocks are smaller, the time steps decreases. The problems in convergence increase when you have smaller blocks and so on. Of course, the results from this to this are much better, but the simulation times is also increase very rapidly. Okay. Well, I have some slides here just show evolution, but I'm going to jump this part here because you can have it in the material. Here, unfortunately, I couldn't find any other source of information about this. Maybe we have some papers in the literature, but just to show you how the evolution of the simulations are on time, for example, from the 60s to today. In the 60s, we used to run models that were up to 1,000 blocks. Then in the 70s, go to 10,000, almost 10,000 blocks. This is this bar here represents the minimum and the maximum studies that were presented in the literature. This was a study from Schlumberger using literature examples, showing how many models they were publishing. For example, in the 80s, the minimum size of a block was almost 10,000, 8,000, for example, to 100,000. Then in the 90s, then in the 20s, and a decade ago was almost something in between 10,000 and almost 1 times 3, in this case 100 million, right? 100 million blocks. Of course, I will not use 100 million blocks to represent a simple reservoir, right? These are reservoirs that are very complex reservoir, huge reservoir, and so on. But this is the average, and this is the variation we have over the. So today we have a much bigger variation here. Of course, because we have simpler reservoirs and have more complex reservoirs, we have simpler computers and powerful computers to run it and have. But today, I would imagine would be something like here, increasing this. This bottom part here is always increasing. It decreased a little bit. It was strange, but should be something like this. The top part also should increase like this, right? And the average also increase like this. So we could make a projection here and say that today we are running something between 1 billion blocks and 100,000 blocks, depending on the size of the reservoir simulation and so on. Okay. Here's just some aspects that we have parallel computers and so on, just showing that we can, for example, reduce the simulation time a lot for the computers today. For example, here is an example decreasing the number of cells in a study from 97 and another from 2004. The same study was published on that, and showing that if you are using 64 processors in the computer, we could be reducing by an order of 10 here the simulation time, right? So it's important also to consider that we have these powerful machines today that can speed up process like one. And for example, the simulation, for example, of the offshore fields in Brazil or the pre-salt, they are huge reservoirs with millions or even 100 million blocks. we need to use these powerful computers if we want to represent all the heterogeneity we have in these carbonate reservoirs. Okay, here I put some challenges, but always accelerate the process is always a challenge. Parallel computing is always a challenge as well, because it's very used today, but it's not very efficient. We have some studies on that, but we have these studies also. It's not so beautiful as this curve here, for example. Sometimes we have a curve like that is like here. Why? Because sometimes we increase too much the number of computers. It's the code of the simulation code is not prepared to that. We spend more time breaking the problem in parts. If you have too many parts, for example, here you are breaking the problem in 64 parts, and then we have to build everything together back. Sometimes the efficiency of and we have to spend time changing information from one processor to another. And sometimes this curve is not so beautiful as it is in this test that this guy did in Schlumberger. Sometimes the curve is like this, and that keep decreasing. So there is an optimal number of processors, and we have to increase the quality of the codes in order to make a better use of these powerful parallel machines today. Going up more than 1 million blocks is still a challenge, even for the companies today. It's okay, but we have to have very powerful machine. It would not be a challenge if you have just one guy running simulations, but imagine that we have each company have hundreds of people running simulations, and they are competing over the same parallel machines, the same processors. So if everybody decides to run 1 billion blocks models, then we have to have a lot of computers. So it's a challenge in terms of not only the computer, but also investment that we need for that. Okay. The integration of other areas is also a challenge, as we can see. It's improving year by year, but is also a challenge. And the data acquisition times real time that we are going to this E-field and digital fields concepts, intelligent wells is also a challenge. If we have time, we're going to talk a little bit about that. But if you remember, in my first class, I talked about that black part, which is the step 12 in our methodology, which is the short-term methodology. We need to improve the quality of these models to reproduce this short-term behavior. It's very important. I don't know if you remember that I told this. Maybe you have a little bit more time at the end of the course to talk about that. Okay. Another challenge for me is very important is the well modeling. That's why I'm going to spend one time talking about this. Almost one class talking about this, because in the reservoir the blocks are bigger, it's 50 meters and so on. But close to the reservoirs, we have to model the behavior from the fluid from the reservoir to the well, and this geometry is complex. And this geometry complex, we have to try to represent the fluid behavior to this geometry, the complexity geometry. And it's important not only because it's complex, but because here is the place where we are measuring production, right? For us, the simulation, reservoir simulation guys, we are concerned about the reservoir. Once they go to the well, it's the amount of fluid that we are modeling, that we are producing for the outside of the reservoir. So if everything is okay, our model is 1 billion cells, we have a very well representation of the geology, I have a very efficient parallel computing and so on. But if my model of how much fluid will come into the well, from the reservoir into the well is wrong, I'm gonna put all this effort of the other parts because I'm measuring the amount of oil and water and gas that is being produced wrongly if you have well models that are not okay. That's why we have to concentrate a lot of attention in the well modeling. Of course, the well modeling is less critical when we have data. For example, when we have a well that's already existing and we have a well test and we have a dynamic data, then we can calibrate the well model. That is not so complex. But for a new field where we have to forecast the production, where in wells that we didn't drill yet, then the well model is very important. And I recommend strongly to put, when you do this type of study, to put uncertainties in the well behavior, not only in the reservoir properties like porosity, permeability, relative permeability, but we have uncertainties also in how will be this productivity, injectivity, and so on. Okay? I will talk more specifically about these well models and how we consider these things in our aspects. Okay. Another challenge today is, I will not repeat, is what João told you about integration, about reservoir and production facilities. And this is a challenge, especially in Brazil, because of the pre-salt and the fluid that we are going to produce, but also for Campos Basin, because we have a very complex production system. And if you are concerned only about the reservoir, this well here is the boundary condition of the production facilities for the well, but it's also the boundary conditions for the production facilities from the well. So the well is an interface between the production facilities and the reservoir. And one is the boundary condition for the other, okay? And if I'm modeling the facilities wrongly, or if the boundary condition is wrong, the reservoir can be very well, the model of the reservoir can be very good, the model of the well can be very good, but the boundary conditions are wrong. So I'm gonna, again, produce the wrong amount of fluid. So it's very important for us to have a good representation of these production facilities in order to have good boundary conditions. And nowadays, we have very complex structures, like we have, in some cases, we are simulating with Petrobras a system called HICEP, which is in the pre-salt, we produce a lot of gas, for example, and this gas is a main limitation of the platforms today. So we have to produce less oil because of the amount of gas that we are producing, because the platform has no capacity to produce the amount of gas. So because of that, we have these limitations, and then they are trying to install this equipment that's called HICEP. HICEP because it's a high temperature, high pressure temperature that we're gonna put in the sea, and they're gonna separate the gas from the oil and re-inject the gas into the reservoir. So instead of taking this gas into the platform, they're gonna re-inject this gas into the oil, and I'm gonna produce much more oil in these conditions. But we have to model all this and specify the boundary conditions in these situations, for example, right? And also, we have conditions today in the pre-salt that we are simulating reservoir from the pre-salt and the post-salt, like this one, for example. Let's imagine that this is a simulator in the pre-salt, the post-salt. I'm simulating this to the platform. They share the same production facilities, so the boundary conditions, what I do in this reservoir will influence the boundary condition in the other reservoir. Sometimes this is a black oil reservoir, this is a compositional reservoir, so I have to put everything in the same model. So this is still a challenge. We have ways to do it, but it's not easy to do it. Okay, I think that is what I was planning to talk to you today. I don't know if you have any questions. I have the applications here, which is the second part of the course. In these applications, I have some slides that I will make it available for you, but I will not talk about this because the applications are the same thing that Manuel, Célio, Alessandra, João, and this thing told you, because I'm not going to repeat it. But as I saw the classes, I have some other aspects. I'm going to give some of the slides, because this would be just an introduction about these applications. And there is no sense in talk about an applications, as we have seen seminars about these topics, okay? But if you have any questions about them, let me know. What I'm planning to do in next class now is to start going deep into the equations. As I showed you today, just an introduction. We're going to take the introduction of the black oil model and show how the simulation works from inside. Okay. So that was all for today. I was planning to give you this introduction. If you have any questions, let me know. I'm gonna stop recording here.